Hello everyone. Today we are going to handle the powerful tool which shows the interactions between particle Feynman diagram. The lecture will follow these contents. Background information first, elements and how to draw for next, examples and scientific meaning for last. Let's see the background information for Feynman diagram first. To learn about Feynman diagram, we should know why Feynman diagram was needed before studying Feynman diagram. The world we are living in consists of a lot of materials. Scientists had a curiosity about what comprised materials for a long time, and they began to divide it. Then they finally found indivisible 17 components like electron or up quark, and people called this elementary particle system as a standard model. From this discovery, people started to understand the quantum science world for the first time. Since then, people reaccumulated all reactions based on understanding interactions of these components. Reaction between particle and antiparticle, beta decay, strong interaction between subatomic particles, and etc. Now people want to find a common tool which is able to express and deal with these reactions simply. For that reason, Feynman diagram finally appears. Then let's move on to the main part. What is Feynman diagram? Feynman diagrams are graphical representations of mathematical expressions describing the behavior of subatomic particles. It contains the interactions of particles which join and split by exchanging their energies as described by the diagram. To explain more technically, it represents a perturbative contribution to the transition amplitude or correlation function of quantum mechanics or statistical field theory. Feynman diagrams help to visualize the interactions of particles simply, what would otherwise be difficult and abstract formula. While the diagrams are usually applied to quantum field theory, they can also be used in other fields, such as solid-state theory. There are some rules when drawing diagrams. First, each line represents the propagator of specific particles, and vertices represent the interactions of particles. Second, arrowed lines represent particles, and lines with arrow pointing against time represent antiparticles. If the particle itself is same with the antiparticle, arrows do not show on the lines. Third, W boson and Z boson and photon could be represented by wavy line. Spirally lines represent gluon, and dotted line represent Higgs boson. In case of need to clearly distinguish some particles, we can indicate the name of particles on the lines. The horizontal axis of the diagram indicates the passage of time. So usually, the initial state is assumed to be at the left of the diagram, and the final state at right. Antiparticles are represented as moving backward along the time axis in diagrams. And the vertical axis indicates the spatial movements. But the x-axis and y-axis can be converted when we draw a diagram. Let's take an example of electron-positron annihilation. This process occurs when electron and positron collide with each other, releasing gamma rays and sometimes other particles. Let's say the initial state of the process is one electron and one positron, and the final state is quark and anti-quark, which has same amount of energies of gamma rays. Matter particles such as electrons and positrons and exchange particles called gauge bosons are represented on the diagram like this. Electron in the initial state is represented by a solid line with an arrow indicating toward the vertex. Positron in the initial states is represented by a solid line with an arrow indicating away from the vertex. Photon formed by the collision of electron and positron is represented by a wavy line. Quark and anti-quark formed through the annihilation process are also represented by solid lines with arrow, and gluon is formed by quark or anti-quark. So far, we have looked at the purpose of the Feynman diagram and the way we can draw it. To add a bit of background information, the Feynman diagram is a concept that started with pictures that Feynman had drawn to explain his logic in the process of conflating QED, which means the quantum electrodynamics theory. So it was natural for other scientists to work on drawing the 4 basic interactions into a Feynman diagram. Except gravitational interaction, Feynman diagram of 3 basic interactions were easily drawn like these pictures. Recently, detection experiment of Higgs particle, which is a particle that mediates gravitational force, has succeeded, so that a Feynman diagram about the generation of Higgs boson has been drawn like this. However, we need to think about the value of the Feynman diagram. Feynman diagrams do not exist simply to just illustrate quantum phenomena easily. Through Feynman diagram, we can explain precise reason why the various quantum phenomena are formed. As an example, let me explain the creation of strong nuclear force and the stability of the atomic nucleus with the Feynman diagram. Well, in the quark level, we can draw a Feynman diagram of p-n scattering, the collision between protons and neutrons, like this picture. In this figure, down quark mainly participates in the collision, and the protons and neutrons exchange pi0. Therefore, the proton and the neutron remain as proton and neutron. But then, what happens if up quark mainly participates in this collision? The proton and neutron will exchange pi0 so that after the collision, the proton changes to the neutron and the neutron changes to the proton. We also can draw this with the Feynman diagram, like this. This conversion of proton and neutron is the essence of strong nuclear power. Just as Benzen's double bonds and single bonds convert to each other and form 1.5 bonds to make stable state, protons and neutrons in the nucleus are converted to each other and form the stability of the nucleus. This essence of strong nuclear force is important scientific evidence to explain the phenomena by atomic nuclear stability, such as phenomena that neutrons that are very unstable when they are independent do not collapse well within the nucleus. So this is our final contents, and thank you for listening.